Lesson 8.3, more on graphing of rational functions, only our rational functions get to be a little bit more complex. So a lot of material in this section. Let's give it a go. First off, I guess a little review. I got y equals 5 over x minus 2 plus 3. That's what we did in 8.2. If I was going to graph that, I'd want to realize that there is a vertical asymptote at x equals 2, because that's what makes the bottom equal 0, and there would be a horizontal one at y equals 3. And then I find a couple points on each side of the vertical asymptote. So I might plug in x is 3. If I did that, looks like I'd get 8. So that'd be up here somewhere. If I plug x is 4, I'd get 5.5, and that ends up looking like this. And then I end up, when I graph this on the other side, I can plug in, say, x is 1, that'd give me -2. And if I plug in x is 0, I'd get a half, and that's going to look like that. So there's just a sketch. Well, in this lesson, they're not going to be in this form where you've got this HK that's staring in the face and is representing a transformation of y equals 1 over x, the parent function. What you're going to have is the version where 5 over x minus 2 is actually combined with 3. So I'm adding these fractions. In order to add fractions, what do I need? Common denominator, which would be x minus 2. So I end up with 5 over x minus 2 plus 3x minus 6 over x minus 2 if I distribute the 3. And this turns into 3x minus 1 over x minus 2. So what I just created right here, if I put that in my graphing calculator, I'm going to get the same graph of what I graphed over here. If it's in that form, are we going to be able to come up with these key concepts, the asymptotes that I came up with on the left? On my original function, I said the vertical was x equals 2, and the horizontal asymptote was y equals 3. Well, when I give you problems like this over here circled in black, are you going to be able to find the x equals 2 and the y equals 3? Well, the x equals 2, that's still pretty easy, because that still makes the bottom equal 0. The y equals 3, I don't know. That's, I see a number 3 right here, but just because there's a 3 there, does that necessarily mean it's y equals 3? And that's what we need to figure out. We're going to discuss that when we turn the page here. How can we determine what the horizontal asymptote is when it's in this form of it, like a simple fraction? Other things we need to be able to come up with are, is the graph continuous or is it discontinuous? And what that amounts to is if there's spots on the graph where it stops going from left to right and then continues on after that. And the one up above would have been discontinuous because you had this vertical asymptote over here, and the graph went something like this. I'm just sketching it. But as I went left to right, put a dot there. If I'm a dot on the graph and I go from left to right, I'm like, all right, I'm fine, I'm cruising right along. But then if I need to get over to the other side, I got to make this huge jump. When you got to make this huge jump like that, that is a discontinuous situation. Continuous would be if it was all connected and there wasn't that vertical asymptote there. Okay, so this is discontinuous because of the vertical asymptote. There's one other thing that can cause discontinuity, and we'll talk about that next. And that other thing is actually specifically called removable discontinuity. So there's two types, removable and non-removable. What I just showed you up above, this was non-removable. When you have the x equals for the vertical asymptotes, that situation is non-removable. I like to call my vertical asymptotes called walls. And I can't really remove a wall real easily, so I call it non-removable. move the wrong wall, the whole house might come down crashing on you, so be careful with that. What is removable is what's called a hole. So sometimes you can find a point that's called a hole. It's actually a hole in the graph. That's a new concept. You get a hole if, well, here I've got a situation where I've got x plus 1 in the denominator, so it looks like maybe x equals -1 is a vertical asymptote. But it's not. It's not right. It is not that because it's actually a hole. You get a hole if when you factor the rational expression and then look to cancel. If what makes it equal 0 in the denominator cancels, that's actually a hole. So this graph right here, this one that I'm working with right here, would have a hole at -1 comma something. Now, the something I could find just by plugging -1 in for x right here and find out that there would be a hole at -1, 1. So if I were going to advise somebody to look out for the hole, I would say there's a hole at -1, 1. There's a hole right here, 1 left. And, oh, excuse me, I did 1. I did -1, -1. We do that. Quick sketch. -1, 1, and 1 left and 1 up. So there's a hole right there. So if I want to say avoid the hole, that's where it's at. Put in your graphic calculator, graph it, look at the table values, see what the point is to cause a problem. So we want to get fairly adept at using our graphing calculator. We want to make sure that when we plug these in, we put parentheses around numerator and denominator. And I'm going to go ahead and plug this one in. Got a couple other things in here already, but I'm going to go to Y3 and parenthesis x squared plus, and I needed to get 3x plus 2, so plus 3x plus 2 parenthesis divided by parenthesis x plus 1 parenthesis. Okay, so if I go to graph that, well, my window's all messed up. I got something to show up. I'm going to need to do a zoom 6 here so I can get a better graph. There it is. And the graph looks like a plain old line. It doesn't look like there's any single problem whatsoever there. Well, if you look at the table, go second graph, you can see that at -1, there's actually an error right here. And you should be able to tell that the number that goes with it is 1 because the Y3, here I got -2, -1, 0. Then there's an error. That would be 1. Okay, so that's where the hole is, -1, 1. And I've tried over the years to get my calculator to show where the hole is unsuccessfully, and I actually had a student figure out how you can do this. Go to Window and realize where it is, -1, 1. So surround -1, 1 with a window that fits it perfectly. What's right around -1? Well, right around -1 that surrounds -1 is, let's try to get, let's see here, -2. Okay, -2 is just lower than -1, and 0 is just bigger. And then +1 is my y. What's lower than +1 would be 0, and bigger would be 2. And then now if I graph that, you actually can see the hole. The hole's right in the middle of the screen there. Okay. So it is possible, no matter what calculator you have here, to get your calculator to show the hole. Over the years, we've tried zooming in to no avail. But apparently, if you pick the integers that surround where the point should be, your calculator will show the hole. Okay? So, we have the table of values, we did that, and we already mentioned what that point was. It was -1, 1. And why does this happen? It happened because the x plus 1's canceled. Which makes it seem like we should just get y equals x plus 2. which would be a line with no problems, but you gotta always look at your beginning, and in this whole chapter here, always look at the beginning. What caused the problem? -1 in the denominator will cause a problem. Okay? Then I just go on to talk about non-removable discontinuity. Again, that's at non-removable. That is when you have your vertical asymptote, that's non-removable. So vertical asymptotes. Also mention the piecewise functions. That's another topic. Piecewise is another example of where you would have to jump to get from one spot to the other sometimes. So those can have non-removable discontinuity as well. But for this chapter, we're going with vertical asymptotes cause non-removable discontinuity.